Dear ladies and gentlemen, dear colleagues, with your permission I am honored to open our last session, which is devoted to public defense by Miss Maria Kиселева of his PhD thesis entitled Oscillations and Stability of Living Systems, Analysis and Numerical Methods. This thesis has been submitted to the Sankt-Petersburg State University for the scientific degree of philosophy doctor in the subject area mathematics. This is an outcome of a postgraduate study at the Department of Applied Cybernetics, the Faculty of Mathematics and Mechanics, St. Petersburg State University, and the thesis was supervised by 3 professors. They are identical to the supervisors of the previous 2 theses, and so, with your permission, I will not repeat them. And all the prerequisites for this defense have been assessed by the St. Petersburg State University with a positive result, and so the thesis has been nominated for public defense. To conduct the defense and to deliberate the degree, final defense committee was appointed by a vice-chancellor of the St. Petersburg State University. This committee was not rotated as compared with the previous 2 sessions, so I hope that everybody is well acquainted to its composition. The prerequisites were also satisfied. These were assessed by the St. Petersburg State University, and so it seems that we have a full range of reasons to proceed to the final defense examination. So the final defense examination is declared open. Dear Ms. Kiseleva, you have approximately 15 minutes for presentation of an overview of your thesis. You're welcome.
Thank you very much. Good evening, everyone. My name is Maria, and today I'm going to talk about oscillations and stability of drilling systems. First, I'm going to briefly talk about history of drill string failures. Then I will consider some existing mathematical models of drilling systems, and yes, particularly the model which motivated my research. Then I will introduce 2 mathematical models developed in my thesis, and I will present analytical and numerical results. Then I will go to conclusion of publications. Drill string failure today is one of the most common and routine events drilling industry faces. It increases the cost of drilling and provokes the loss of valuable drilling time. Drill string failures have been studied for many years already, and considerable results in decreasing those failures have been achieved. Here is some statistical data which shows that. For example, in 1985, 45% of all deep well drill string failures or problems were related to drill string failures. And in 1991, it was stated that one specific drilling unit could experience up to 5 failures within just 2-month period, and the cost of each failure could be more than $2 million. In 1994, the drill string failure prevention quality improvement project was implemented. That allowed to dramatically reduce non-productive time costs from $6.5 million to less than $1 million. And it also allowed to reduce both twist-offs and total failures by 75% and 55% respectively. Nowadays, the situation is as follows. The drill string failure occurs at some point on 1 out of 7 drilling rigs, and the average cost of each failure is around $100,000. So the problem still remains critical. In order to better understand mathematical models of drilling systems, we need to know how real drilling equipment works in general. So the borehole is created by a rock cutting tool called drill bit. The drill bit represents a short, heavy segment with a cutting device at the free end of it, and it's driven by a torque created on the surface by a rotary table. The rotary table is driven by the motor via transmission box, and it acts as a storage of kinetic energy. So this energy is transmitted to the drill bit via the drill string, which mainly consists of drill pipes and could reach up to 8 kilometers in length. And the lowest part of the drilling system is called bottom hole assembly, and it consists of drill collars and the drill bit, and can reach up to several hundred meters in length. Now I'm going to move to consideration of the model which motivated my research. The researchers from Eindhoven University of Technology constructed and studied the following experimental setup, which is a rotary setup, and it can be recognized in real drilling systems. So the setup consisted mainly of the following parts. The upper disc, which is actuated by a motor, is connected to the lower disc with the steel string, which can experience torsional deformation. And there is also a brake device acting on the lower disc in order to model the friction torque. There are also other types of mathematical models of drilling systems, and they can be found in the works listed over here, for example. We are going to look at this model. The model is described with the following differential equations, and we note that these are ordinary differential equations which have kind of simple structure, and that allows us to make some analytical research of the system as well as numerical research. Over here with red, we mark the torque which means the upper disc of our model. So, as I mentioned before already, the simplicity of equations allows us to make qualitative analysis of the system. But the minus of the system is that it lacks full dynamics consideration of the electric motor. So in my work, I'm going to introduce new equations which will have more full equations of the motor. The first model, the first mathematical model, it is assumed for this model that the drill string is absolutely rigid. Thus, the mechanical part is a bit simpler than in the previous slide, but the drive part is described with more complex equations. And the friction torque representing the load acting on the lower disc is represented by the resistance torque of the column side. But this torque is torque with the asymmetrical characteristic in comparison with the classic column type friction torque, which has symmetrical characteristic. Note that over here we use the differential inclusion sign, since the characteristic is discontinuous. Performing the non-singular change of variables, the system of fifth order can be reduced to the system of third order. And in order to define the model on the sliding mode on the discontinuous surface, the following Philippine definition is used. For this model, the idle speed operation mode was studied when actually the drilling doesn't take place, and that corresponds to the case when the drill rotates with a speed equal to the speed of rotation of the magnetic field created by the stagger of the rotor. And then the local analysis was done for the case when actually the drilling process takes place. Here, two cases were considered depending on the value of the speed of rotating magnetic field. And in order to demonstrate better demonstrate the equilibrium states of the system, the static characteristic is quite useful. The imprisoned part shows us where the stable equilibrium states, and in contrast to that, the decreasing part shows the unstable equilibrium states. Over here, the particular interest is stable equilibrium states, since they correspond to the operating mode of our system when the drill rotates with constant angular speed. The second case, and we also consider the case of sliding mode. The system also has an asymptotically stable equilibrium state for gamma more than maximum static characteristic. The system experiences abruptly changeable loads, so it is necessary to understand what happens to the system after the trenching process. For real system, that means that when the rock is changed, we need to understand whether the drilling system will continue to function in a normal way. Mathematically, this problem is stated in the following way. We have the first bedrock to which gamma 0 corresponds, and the second bedrock to which gamma 1 corresponds. For the first bedrock, we have the stable equilibrium state, and it is necessary that the solution of the system with initial data corresponding to the first bedrock equilibrium state, stable equilibrium state, would tend to the equilibrium state in the new case with gamma 1. So the conditions on both parameters are formulated in the following theorem. And there are also two corollaries. The first corollary is presented for the case when the speed of rotation of magnetic field is equal to the maximum of the static characteristic. And the second case is considered for the situation when also the drill is allowed to rotate only in one direction. In this case, both analytical and numerical results were obtained, and during the numerical computation, it was obtained that actually the limit value of the load can be defined as the maximum load under which the system has stable equilibrium state. Now I'm going to consider the second model. This is a double mass model, and it already has more full equations of the mechanical part. So here we assume that the drill string can experience actually torsional deformation. Performing the non-singular change of variables from our model of 7th order, we can obtain the system of 5th order. For this system, we also considered the idle speed operation, which corresponds to rotation of both disks with the same angular speed without relative displacement. And the local analysis of the system was provided. In order to provide the further analysis, the friction torque of a column type, as before, is considered with non-symmetrical characteristic. And here we use again the Philippine definition in order to define the behavior of the system in the sliding mode. So here again, two cases are considered depending on the value of the speed of rotation of magnetic field. So we have both asymptotically stable equilibrium and unstable equilibriums in this system. Stable equilibriums corresponds to operating modes, which are when the upper and lower disk rotate with the same angular speed and with constant angular displacement. And also the sliding mode was considered, where also asymptotically stable equilibrium state is found. For this model, further, we introduced the friction model, which was used by the researchers from Petrovский University of Technology, which has nonlinear structure. And in this particular case, we studied the behavior of the system varying the parameter T0. And here is the bifurcation diagram representing the results. Particular interest, so in this system, both stable equilibrium states were obtained. There were cases when you have unstable equilibrium states, but there also is a very interesting region where both stable equilibrium state and stable limit cycle appear in the system. This means that the system has so-called hidden oscillations. Hidden oscillations are the oscillations based on attraction of each doesn't contain small neighborhoods of stable equilibrium states. Thus, it is quite hard to localize those oscillations. Further, I'm going to demonstrate how they look like. So, the standard computational procedure of oscillations would be we first define the equilibrium states of the system, and then we mainly localize the oscillations by starting the trajectory in the neighborhood of unstable equilibrium. But over here there is a case when we have just a stable equilibrium state and stable limit cycle. So we need to know how to pick the initial data. Over here the following recommendation could be given to check the neighborhood of sliding mode. So here are more pictures, and my conclusion is I considered the history of adjusting failures in oil and gas industry. Then I introduced the model which motivated my research. Then talked about the two mathematical models which were developed in my thesis. And for both, for the first model, with the analytical results were obtained, and both numerical results as well. For the second model, we obtained so-called hidden oscillations. Here are my publications. Thank you very much for the attention.
Thank you very much. The situation with responses to the series is identical to those with the first two surveys, so we had nothing to do but to proceed to public discussion. Dear Professor Tikhonin, would you please to open it?
So once again, I want to thank for a very clear presentation. Also, the written presentation was very nice and tutorial in a way we like to be in Finland. In fact, I have very little to ask about the technical content and details, so rather I want to discuss with you about your insights of generalizing and extending the work. So you have produced two different models, made some theoretical work with one and mainly numerical for the other. So starting from the last model, you have found hidden oscillations, and I guess these are related to the interplay of the torsional flexion of the drilling device and the friction model. So, what is your view, how the dynamics of the electrical engine, how does it affect the fact of having hidden oscillations? So do you have more or less hidden oscillations if you have real engine dynamics in the system?
Well, it definitely affects, but I think the main, what mainly causes the oscillations is the way the friction torque looks like.
Yeah, I agree with that. But whether the motor is sort of damping this or enforcing it, do you have any feeling of that?
Not really. I mean, in the previous model, there were also some oscillations.
Yeah.
So, yeah, I think it's mainly the friction torque, basically this region, following region.
So I guess it requires sort of further study to see whether hidden oscillations are more frequent or less frequent in either of these models. Of course, one way to approach it might be to make sort of asymptotic type analysis of having a very powerful motor or having very rigid motor and going to the limit and seeing how it qualitatively affects to this hidden oscillator. And of course, maybe also observe the electrical engine related variables within these hidden oscillations. What happens in the engine when there are hidden oscillations in the bottom end? And I guess a bit similar thing. So whether for this sort of rigid drilling, whether you can think of extending the theoretical results by assuming a drill that is almost rigid, so that is sort of singularly perturbed version of a rigid one, that has maybe simpler dynamics than your full model, but that's amenable for analysis.
Some further research could be done, yeah.
You mentioned that it's very hard to find the hidden oscillations, so do you have any Monte Carlo type statistics on the probability of finding hidden oscillations? So how frequent they are in the operation regime?
Well, we didn't really. The idea was to find the oscillations themselves, and we considered just a set of parameters. It's kind of big task because there are a lot of parameters in the system. So the only recommendation that could be given for this model is to check the sliding mode every time, the neighborhood of the sliding mode, because the oscillations over here are of the stick-slip type.
Okay, that concludes my part. Thank you. Professor Redman.
Well, a strange coincidence. 2 months ago I was in a thesis examination commission on the same subject of drilling systems in Mexico, but there was some other model of the drilling systems of the torsional vibrations. The model with distributed parameters, that is, your drilling axis was considered as a beam with distributed parameters. So, but at the same time, the friction model was almost the same. This showing that this is a normal model for doing this. My question is as follows. Since we have at our disposal, at my disposal at least, 3 models, that is 2 of yours, plus the distributed parameters that I know, and that if you would like, I can send you the full text of the thesis. My question, of course, goes to your 2 models, or yours that is in your thesis, because the third, you don't know it yet. What connection you see between the 2 models, that is in the following sense, because you mentioned at the end the features of each model. Could you deduce, by simplifying, for instance, some small time constants, one model from the other?
Yes, the first model is just a simplification of the second model, because it just assumes that the drill string is absolutely rigid. So we basically need to take into account the displacement in the second model in order to obtain the first one. So that's the connection. And
to continue this difference, because the hidden oscillations were observed in the second model after adding the other dynamics.
Yes, but we also added another friction torque. For the first model, a more simplified torque was studied since we wanted to get some theoretical results.
And these oscillations, to continue the question of Professor Tikhon, they were felt at the beat at one age of development, but not the state variables of the induction motor did not oscillate.
Yeah.
They were on some steady state. They were,
no, the whole thing was oscillating.
oh, everything was oscillating?
Yes.
Everything. Because in this distributed parameter model, there was no report of such oscillations. It's true that they were reporting to failures of the drill, and when it fails, nobody thinks it's just a failure and destruction. Everything is destroyed. Thank you.
Yes, my first question is about the first model. I will speak without this device. I hope you will hear me. You can estimate this maximal critical load, so until you reach it, everything is very good. You have this asymptotically stable equilibrium state. Okay, but when you reach this value, when you go outside this main, can you predict what may happen with the system? Are there ways, at least qualitatively, to describe what may happen when you exceed the critical load?
Well, actually, that means that the load is just too big and the drill gets stuck in the bedrock. Also, the numerical simulation proved that point as well.
Well, thank you.
In the proof of the maybe explain us how you construct this function. What is main idea for construction this Lyapunov function?
Well, there is no general method for constructing, but usually the squared variables could be used, the combination of squared variables. And over here, we also use the integral of static characteristic. So that allowed us to construct the Lyapunov function.
Quadratic form plus integral?
Yes. Yes.
This first.
Actually, I know the papers by Maria very well, because I'm have some experience in doing research in the field of drilling, and I would like to address my words first of all to the Commission, just to explain that the length of the drill string is nowadays is up to 12 kilometers, and you can imagine this is a tube with approximately 10 or 11 centimeters in diameter, and the thickness of the wall is 1 centimeter. Can you simply imagine such system, which, if you even reduce all the geometric parameters in 1,000 times, then we will have 10 meters or 12 meters, and instead of 1 centimeter, we will have 10 microns. So it's a web. So it's hardly possible even to imagine the escape of the problem, and just the failure of the drill strings, the cost of the failure per year is something about $6 billion failure, because for the oil and gas industry. So the problem is it's a huge problem, and as I mentioned, I'm familiar with the papers of Maria very well, and so that's why I'm asked a very simple question concerning the, you use some information from Eindhoven University of Technology.
Yes, right.
Could you please to say some words about this setup, how you get this information, the friction, torque, and something like this?
Well, as I said before, the researchers from Petoskey University constructed the experimental setup, and that allowed to obtain the way the friction looks like, and then just to model the behavior of the friction and to get the expressions for the friction. So, and from there I also get the parameters.
Thank you.
Thank you for very instructive comments.
In the setup of the Eindhoven University of Technology, the direct current motor is used. Please, why have you considered the induction motor in your work?
Well, there are some patients which are listed in my work where this type of motor can be used in drilling systems. So the idea was to implement the model, and we picked this one.
Thank you. And dear members of the committee, we proceed to the irregular part of our discussion. So, any questions, comments, inquiries?
To point the following things and to put then my question, because things go also to numerics, to simulations and so on. Due to your discontinuity of the friction force, friction torque, you mentioned that you needed to define the solution of your differential equations in some sense. And in the written material, you start from the classics, Marchot-Zaremba, contingent equations, to arrive to the Filipov sense of the solution. While the sliding modes you mentioned, they could be tackled using the completed nonlinearity that is a feature of the St. Petersburg University School of Leonov, Killing, and so on. But my question is as follows. Among all these definitions, the Filipov solution is known to be the most stable with respect to numerics. That is, for instance, you need to define, to make myself more clear, you need to define to the solution in your problem, let's say an optimal control problem, probably the best solution would be the definition classical in the Kara-Teodori sense. But when you start to integrate numerically, your integration goes to the Filipov solution, even if you don't want it. The question is consequently as follows. How did you select the integration method in order to cope with your definition, and additionally, this comes to my mind now, did you find the Filippo solution or something else?
So, the method was picked for modeling, especially Filippo definition, and it's described in the article mentioned in my work of Pironin and Kuznetsov. In that particular method, considered two discontinuities which are considered in the first model. So it was good for me to know how to use the method, and also the case of one discontinuity. So that's how basically the method was picked.
And you found exactly.
They tried to yes, numerical.
Not surprising.
Yeah, I would like to continue about this because as your hidden oscillations, they are this stick-slip type. So they play around with this discontinuity on friction. So I guess what would be needed is the sensitivity analysis of hidden oscillations as a function of friction modeling, its regularizations, its discretizations. So whether you find the same hidden oscillation, even if you, for example, smooth out the friction model by small parameter to make it continuous, well-defined, and so on. So this kind of thing should be done so that you're sure that you're not finding numerical artifacts.
So, well, in my research, I've just removed parameters in some area in order to check whether the oscillations still remain, and they do remain in some area. So that was done.
Are you satisfied?
Again, about the oscillations, because maybe it's the most interesting thing we see here. As far as I understand, there are other researchers who studied the model close to that. This Cohen group, did they study? Did they have something like that, theoretically or numerically?
Yes, they did. They had similar oscillations of stick-slip time, so they're pretty correlated with my work.
About hidden oscillation, do you have some idea what is boundary between stable limit cycle and stable fixed point? What is boundary? It's unstable manifold?
Well, in this particular case, there are no unstable equilibriums over here, so maybe yes, there is a boundary of unstable manifold, but actually over here for localizing hidden oscillations, we were taking initial data near the discontinuous surface. So
You found this boundary, no?
Sorry? Numerically? No, we weren't looking for it.
I wonder if it's possible to extrapolate the parameters obtained, let's say friction parameters obtained by encoding universal technology to real systems. Is it possible? How do they correlate?
Yes, they do, because they were using the real system, and for the second part of my system, the induction equations, I also tried to use the real parameters of the induction layers.
Why have you focused your attention, namely on rotary drilling systems?
Well, there are also other types of drilling systems. If we talk about the way how the bore is built, hammer type, sonic type, torque drive type, but the rotary systems are quite common in oil and gas industry. That's why we picked this type.
More questions? So, Ms. Kiseleva, you may take your seat. And at this point, the rather virtual part of our work is closed. And the committee withdraws for the deliberation of the debate. Ladies and gentlemen, please take your seats.
Должны же быть потом какие-то документальные следы защиты.
Dear ladies and gentlemen, dear colleagues, after deliberation of the degree, the final defense committee has come to unanimous consent on the point to be judged. On behalf of the committee, I am honored to announce the decision. The final defense committee recommends the Chancellor of the St. Petersburg State University to confer the scientific degree of the Doctor of Philosophy on Miss Maria Kiseleva. Miss Kiseleva, my warmest congratulations on this.
Thank you very much.
And you have an opportunity to say several concluding words if you want.
Thank you. I would like to thank the chairman and all the opponents. I would also like to send my deepest thanks to my supervisors for their guidance and support. Thank you.
Thank you. And at this point, the final defense session is declared closed. Thank you, everybody. Thanks. Many thanks.
Once again, congratulations.